everybody, welcome to our Rutronik webinar series, Rutronik Connects. My name is Heike Kubisch and I'm a corporate product manager within the wireless department of Rutronik. Within our webinar series about Wi-Fi technologies, you'll learn all about the latest Wi-Fi 6, Wi-Fi 6E and Wi-Fi 7 standards. Today, I would like to welcome Finn Boetius from Nordic Semiconductor, our long-term partner for wireless parts, with the topic about low-power Wi-Fi. The duration of our webinar will be around 45 minutes today. Questions can be typed on the right sidebar. We will answer them at the end of our presentation, and in addition, the presentation will be recorded, and afterwards you will receive the slides from us. So, hi Finn. Oh, we still can't hear you.
It's not a good sign.
No, it works. It works.
Test.
Sounds good. It sounds good, yeah.
Okay.
So you can go on.
Good. Please interrupt me if my sounds start not being there. I will share my screen now. I hope you can see it.
Yeah, we can see. Now your microphone doesn't work anymore. Yeah, now.
Okay, I'm just gonna use my built-in microphone. Sound might be a bit worse, sorry for that. I hope this works and you can hear me more or less. Let me just get my slides back. Yeah,
it sounds good.
Sorry for the technical difficulties. Good. So I'm here to talk about low power Wi-Fi today. To my background, I'm an industrial engineer, so electronic engineers, but also a master craftsman electrician. So I look at the smart home from two different sides, basically, which is why that is one of my areas next to Wi-Fi and Thread. I'm very happy to answer your questions at the end, so please put them in the Q&A box, and we'll have a look at them at the end of the webinar. I have about 39 slides, I think, so I'm gonna try to be relatively quick and get through this. And everything should be available afterwards for download, I think. So, quick agenda. What do we want to do today? I'm going to start off with a brief introduction of Nordic Semiconductor, in case you're not aware what we do, who we are. I promise it's just 2 slides. Then we're going to have a look at the Wi-Fi market and the part of that market that we are interested in. We're going to have a look at the challenges for low power Wi-Fi, how to solve those challenges. And then we're going to look into Wi-Fi use cases and what Nordic has to offer in terms of products. So, Nordic, a very brief overview. We are a fabless Norwegian semiconductor company. We are mostly known for making everything that's low power wireless. We are doing a lot in Bluetooth, in Wi-Fi, in cellular, and we also have power management ICs, some cloud services. We are headquartered in Norway and Trondheim, but we have offices basically all over the world. Some of the really nice things about us, or what we're known for, is we have a very active and well-working tech support. And we focus basically all we have on low power and wireless and try to communicate to engineers and not necessarily to managers. So from engineer to engineer is often what you get when you consume any Nordic content. This is our brief overview of the portfolio that we have. Here on the side, you see multi-protocol SoCs. These are usually our Bluetooth SoCs that also support things like Thread, like Zigbee, and of course enable technologies like Meta, like Amazon Sidewalk, and so on. We have Wi-Fi, which I'm mostly going to talk about today. And then we also have cellular IoT. Both Wi-Fi and cellular IoT fit well to cloud services. So we also offer cloud services that work with that. We have power management, and the part that's relatively small in here, software and tools. That is a very much bigger part in reality. So at the moment, we actually have more engineers working on software than we have on hardware. So like we very much focus on supplying our customers with the best possible software solution. And then the tech support that I mentioned before. Good, that was all about Nordic. Let's have a look at the Wi-Fi market. I looked at one of our market research papers that we're getting to give you a brief overview of the Wi-Fi market. In total, it's about 3.5 billion devices. You don't need to read any of the stuff down here. It's just to give you an idea. So the annual growth is between 3 and 5%. But if you now actually look at what we write down here, this is like smartphones, this is tablets, this is notebook PCs. None of these are actually low power. Right? In a smartphone, yes, it's a battery-powered device, but the main power consumption is not going to come for the Wi-Fi chip. So there, you don't really care about being low power in Wi-Fi. So we're going to look at just low power applications. And what I did is I just took this Excel sheet, I removed everything that does not look like low power and ended up with a bit smaller list. By the way, I keep the red line here the same. Well, like on the same page, just the overall numbers change a lot. So from 3.5 billion, we go down to about 1 billion devices. And now here we have things like smartwatches, like game consoles, like smart plugs, IP cameras, things like that. So more things that are focused on low power. The interesting thing here to see is the annual growth goes up to about, so like this is the overall annual growth, not the absolute, but the relative of the whole Wi-Fi market. So here we see the low power Wi-Fi market is growing a lot stronger than the overall Wi-Fi market, which makes completely sense, right? But the main point I'm trying to make is a lot of products are transitioning towards low power Wi-Fi, which is very nice for us since what Nordic does is being low power and wireless, but it's very nice to see. So now we want to go into the challenges, and I promised someone I'm gonna rant a bit about why Wi-Fi actually isn't very well suited for low power. So we're gonna go into all the problems that you run into when you try to make Wi-Fi low power, and then we're gonna have a look at how to solve that. So I'm gonna start off with inflexible power save modes. So if I buy a Wi-Fi device and I connect it to my Wi-Fi router at home, that device will not be able to choose how long it sleeps. So the sleep interval, if at all, will be dictated by my Wi-Fi router that I have behind this wall that I'm sitting next to. So as a device manufacturer, you can't control how long your device will be sleeping. So it's very hard to actually control the power consumption of a Wi-Fi device. And you can't actually expect a customer, because like not even my colleagues who are mostly working with low power wireless, most of them don't actually change their Wi-Fi settings much. You might change the channel that you're using, you might change some security settings, but very rarely are people actually going into power save settings. So we can't expect the normal customers to change Wi-Fi settings if you have consumer customers. It's a whole different story if you're talking about industrial. You have very congested bands. You've probably heard this a lot. So you not only have different Wi-Fi networks, like if I look at Wi-Fi networks right here where I'm sitting, it's probably like 30 Wi-Fi networks that I can just see on my phone, just from my neighbors, which obviously makes the band quite congested, but it's not just Wi-Fi, it's also Bluetooth, it's also Zigbee, it's also Thread, it's the microwave, if one of my neighbors tried to use that. So like there's lots of stuff happening on the 2.4 gigahertz spectrum, which makes longer wait times for end devices, which means if you have to be in receive mode longer, you'll use more power, which means your battery is going to drain faster. It also means more retransmit, and it makes the whole system less deterministic because you don't necessarily know when your message will get through. So it might be you might need to retransmit it. And not everything in there is Wi-Fi, so you can't actually control that part very well. This is a thing that I've seen a lot when driving on the Autobahn in Germany. We have a word for this in German. It's called Elefantenrennen. So it's an elephant race. And this is a very good example of how Wi-Fi routers work and the pain for low power devices. Because the oldest and slowest devices dictate the speed. So if we have this truck driving 82 kilometers and this truck driving 80 kilometers, they will take a very long time blocking this whole road. So let's have a look at this poor guy here. He's our example here. He just had a really long day doing presentations about low power Wi-Fi. He just wants to drive home and go to sleep to save power. But instead of driving home at a relaxing 200 kilometers an hour on the Autobahn, he has to wait for this elephant race and stay awake for longer, using precious time before finally entering sleep mode. And the same thing is happening in our Wi-Fi routers, because a router is set up in a way that it wants to enable most of the devices to work, which means very old devices need to be supported. And that means, very slow overall data rates, which for your new devices, if you're building them, means they have to stay awake for longer and listen for longer since the data rate is lower. My second analogy is backwards compatibility, and this is basically the same problem. Backwards compatibility is not very good for low power Wi-Fi devices. Here as an example, I brought this light bulb with this E27, which for a consumer, this is really nice, because at home, if I just want to exchange my old light bulbs for new LED light bulbs, this is perfect. I can have everything the same. I just take out the old light bulb, switch in the new light bulb, everything's great, everything works. It's a very different story for a device manufacturer. For a device manufacturer, you need to make sure that you have a power conversion in this little thing that goes from 220 volts or 120, depending on where you are, or 230, down to very small DC voltages. You have to have the LEDs in here. And there's a lot of energy being lost, even though they're a lot more power efficient. But there's also a lot of heat being produced in this part, which means for the device manufacturer, you need to buy special parts that can handle heat very well. And there's lots of extra things that make this a lot more complicated to design than just designing a full new light fixture. Oh, this reminds me, if you're in here and you've did one of these projects before, I tried to figure out how much of the energy is actually wasted in conversion in an average light bulb. I couldn't figure it out. So if you know, write it in the chat. I would be very interested in the actual answer. I've heard different things. But like just the fact that you sometimes need 125 degrees ICs in here tells you how efficient these light bulbs are in conversion. Same thing happening to Wi-Fi routers, because for an end customer, it's very convenient that if you buy a new router, all of your 10, 20-year-old Wi-Fi devices will still work. But as the device manufacturer, this is not necessarily good for you, because if you want to have a low power Wi-Fi device, the manufacturer of that router is not incentivized to support you. Because if I buy a router at home, I expect the number one thing I expect from that router is to supply all of my Wi-Fi devices with internet, which of course the router does. But this also means the overall speed and the router itself is mainly focused on connecting most devices. It is not focused on having my batteries last long. And the router is not incentivized to do this at all, which makes it for you as a device manufacturer very hard to make proper low power Wi-Fi devices. This is my Wi-Fi rant over. Now let's have a look at how to actually fix this. And a real big chunk of these problems are being fixed by use 5 gigahertz. So if you look at 5 gigahertz, it gives devices, or the best thing to do is just use both 2.4 and 5 gigahertz. Then you can, wherever possible, use 5 gigahertz. And where not, you still have the 2.4 gigahertz as an option. And even in antenna design, a lot of the time you can just use the same antenna for 2.4 and 5 gigahertz. Yeah. And access points have been supporting 5 gigahertz for a long time now. So most customers' access points actually will support 5 gigahertz. A good example here is if you have a normal DTIM and other multicast communication that is done at the lowest data rate at the network. So usually 1 megabit per second for 2.4 gigahertz or 5.5 megabits per second for 5 gigahertz. And this is just because 5 gigahertz devices are newer. So there's no reason to support very, very low data rates. These aren't even supported for 5 gigahertz devices. This has many benefits, but the main benefit for device manufacturers in this case is you will have to stay awake for a lot less time. So yes, using 5 gigahertz has a higher peak current and power consumption. But also if you have a DTIM of 1 and your beacon interval is 400 bits, you will need to stay awake for 1.57 milliseconds on 5 gigahertz as compared to 3.29 at 2.4 gigahertz. So you're actually consuming a lot more power if you're using 2.4 gigahertz. And this is without any traffic on the Wi-Fi network, which usually isn't the case. Yeah, and obviously you have a lot more possibilities when it comes to determinism because there's a lot less non-Wi-Fi traffic on the 5 gigahertz band. And even then, there's the whole bandwidth on the 5 gigahertz band is a lot bigger than the 3 non-overlapping channels you have on the 2.4 gigahertz. So a lot of these problems are fixed by just use 5 gigahertz. But then what are the solutions you can use that aren't explained by just use 5 gigahertz? I mainly want to highlight 2 of them here. One is target wake time, which is a power saving scheme introduced in Wi-Fi 6 that is supported by most routers these days. And OFDMA, which is orthogonal frequency division, multiple access, which I have some extra slides on. Target wake time, I just have one easy slide to explain this. And let me actually check how I'm in the time. Okay, I still have some time. So the basic thing is you can see different things here. This would be a device in connected mode. This would be a device in legacy power saving mode. So this is the option you have when you're not using target wake time. Here, the sleep interval will be always dictated by your router. So yes, you can change this in the router settings, but as I mentioned before, I'm guessing most of you listening to this right now never changed any power saving settings in your router. And then in target wake time, what actually happens in this power saving scheme is when a device connects to the access point, they will negotiate a wake up schedule so that your device that you're designing could say, I want to be asleep for 1 second at a time before I'm listening the next time. And, or in this case, 10 seconds. And that can enormously reduce the power saving, reduce the power consumption. And you also have control over how fast your device will respond versus power consumption. So here you actually have an option to determine how often or how responsive your device is going to be. And the really nice thing that most of the time isn't talked about for target wake time is you can also make sure that devices have a specific interval where they are going to listen to, where other devices are not going to talk. So there's even less congestions when you're doing this, or less congestion. Orthogonal frequency division, multiple access. I am trying to put this very simple. So what you can do, sorry, I brought some tea because my throat isn't doing the best. This is a very nice scheme, especially if you use lots of devices that do not send much data, which I'm assuming basically every low power Wi-Fi device is going to do. What happens is you can divide the whole Wi-Fi channel, or one Wi-Fi channel, in this case 20 megahertz, that's the default. You can divide this in 117 subcarriers on both sides. And then you can tell a device to only use a subset of this spectrum, which has the really big benefit that you can have 10, 20, 100 devices using the same channel at the same time. So basically a device will know to just listen to several of these subcarriers and will only get the information on those subcarriers. As you can imagine, this can drastically reduce the congestion on a Wi-Fi channel. And as end device manufacturers, the really nice thing for you is, yes, this is kind of complex. As you might imagine, there's some Fourier transforming involved, but also all of the complexity for this is hidden on the access point side. So it's really easy to implement for station devices, so for end devices. I have a good analogy here to stick with the cards as we had before. If you don't use a scheme like this, what happens is you want to send one package for one device. And that will block the whole channel, which is the equivalent of putting one box into a truck and driving it where it belongs to. When what you could actually do is load the truck full of packages that get delivered at the same time, which is what I'm trying to show with this picture. So if you know you will be in a situation where you have several devices in a Wi-Fi network, or where you're using low power, OFDMA is, I would say, a must use. And with that, let's go into use cases for low power Wi-Fi. So where do we actually see it being used? For us, the very obvious one, and the reason why we initially went into Wi-Fi, is because a lot of our existing Bluetooth customers are already using Wi-Fi. So Wi-Fi and Bluetooth is a very, very, very common combination. First of all, because Bluetooth is, in my opinion, by far the best way to commission a device into a Wi-Fi network. So you have a secure way to commission a Bluetooth device, a Wi-Fi device, by using Bluetooth without needing any user interface other than like one button that says try connecting now or open Bluetooth. And everything can be done with a phone, which literally everyone has at home. Yes, so and then also when you have both in a device, you can use Wi-Fi to increase the throughput and would use Bluetooth for minimal power consumption. An example there's if you have a smartwatch, for example, and you go running with it, and maybe you even have it for a day or two when you go hiking, it's going to collect a lot of data on where you've been, what you've done. And you usually just, while you're on your way, you want to have minimal power consumption, maybe sometimes send some information to the phone, but you don't really want to send all of the data at once. But then if you need to send all of the data, let's say you arrive home, your watch realizes it's in a Wi-Fi network, then you can dump all of the information that you've collected very quickly over Wi-Fi. Or if you need to do a firmware update or something, for example. Also, you have interoperability with phones, very obviously a Bluetooth thing, but also larger ecosystems, smart homes and industrial networks usually rather run on Wi-Fi than Bluetooth in this case. And you have really good security for data with WPA3, and you have secure pairing with Bluetooth. So like this is a very, very good and powerful combination, which I'm guessing most of you are already aware of. Another really nice use case that's very close to my heart, because I've spent a lot of time looking into this, is Wi-Fi and cellular. And here you have different use cases. The one that I'm most excited about, and that's just super cool to me, is Wi-Fi locationing. So using Wi-Fi as an alternative to GNSS. And this doesn't necessarily work the way you might think. Because what we're doing is we're not connecting to any Wi-Fi network. This is, by the way, how your phone most of the time figures out where you are at the moment. So a device can scan for nearby Wi-Fi network. So just checking which networks are close by, not connecting to anything, just checking which networks are close by. use that information, send it to the cloud, usually via a cellular connection. And then in the cloud, there's big databases that can give you your location back just based on the Wi-Fi networks that are nearby you. And this is a lot more accurate than you might think. I have an extra slide on this. So this is my favorite use case. It's just so, yeah, just a very fun implementation. And it's really good because usually, especially in those areas where GPS doesn't work well, like in a building, for example, you tend to have Wi-Fi networks. So this is, yeah, a very good combination with GPS or GNSS in this case. Another use case would be offloading a cellular connection. So if you have a device that's usually connected via cell tower, but it also has a home it goes to. So let's say you're tracking battery packs that your construction workers are using because they tend to get stolen. So you would track them when they're on a construction site. You would use a cellular connection that just sends every hour, every half hour, information on where the device is at the moment. But if then that device returns home, you can connect to a Wi-Fi network and you don't need to use that cellular connection, which can be quite expensive. On the other side, you can also use cellular as a fallback for when the Wi-Fi network fails. So let's say you have a device that has to do some surveillance, but also needs to be able to report back if something goes wrong. Let's say you have a water leak detector somewhere and the power goes out in that area while maybe even due to a water leak. You want your device to still be able to report that back home. And there you can use cellular as a fallback for when the Wi-Fi network fails. So this is a nice combination in several cases. It's worth mentioning here that I say 91 series here, so our cellular SIPs together with the 70 series. The last two use cases, you would need an extra MCU next to it because the 91 series doesn't have enough space for the whole cellular stack plus Wi-Fi, but we do support this use case just using the 91 and 70 series. This is how the Wi-Fi locationing would work. So you basically just scan for nearby Wi-Fi network, send it to the cloud, cloud sends you your location back. This is how accurate it is. So we did a test. And here you can see this is the green line. Here's the GPS line. So this is basically your exact location. And then we've compared it to how does this look when you try to figure out based on cell location, so which cell phone tower is close by where you are, then you get this blue line. And the Wi-Fi line is actually very close to spot on in most of the use cases. And it's very low power very low power in power consumption. Here I broke this up a bit more. So if you want to look at power consumption, like unassisted GPS is very high in power consumption. You have ways to reducing this by giving extra assistance and prediction data to the end device. But still, GPS is quite high in power consumption always. Wi-Fi or using Wi-Fi will be a lot less in power consumption, but still pretty accurate. So here I have average values that you can see how accurate this is. And you will, as I mentioned, you can have a look at this even after the webinar. And then the most power saving way, but also not as accurate, is just looking which cell phone tower is close by. Yeah, I'll switch this. I skipped this slide since I'm a bit late in time. But this is just an example of how long the battery life would last using different methods. Oh. I have an animation that I'm also going to skip. This is one more part that I would like to point out. So even if using Wi-Fi scanning, there's even more ways to save more power by deciding on which channels you want to scan. So we have a scan API in our NF Connect SDK that is very granular in how much power you can consume depending on what you want to do. And if you have a look at this, the one thing that I got really confused by when I saw it for the first time is passive scanning actually consumes more power than active scanning. which means having a device out in the field that just randomly listens to which Wi-Fi networks are close by actually tends to consume more power than active scanning. The main reason for this, so this does actually make sense. The reason is if you do active scanning, you just basically yell out once who's nearby, or the Wi-Fi networks answer you. So you need to not stay connected for too long. Here, you spend more energy because you're listening for a longer time. Yeah, I know I'm rushing through this a bit, but I want to get the information out there. When it comes to low power Wi-Fi, obviously everything is connected in our NF Connect SDK. So if you're using Nordic hosts, you will always be able to use everything. But we also have a Linux driver. So if you're using Linux host and you want to add Wi-Fi to it, there is an option. We're actually even working on upstreaming this to the main Linux. Same for Zephyr, which you should be familiar with if you're familiar with Nordic. But we have our whole Wi-Fi driver directly supported in upstream Zephyr repository to the point where our NF Connect SDK drivers are actually based on what we now have upstream in Zephyr. So you're not tied to Nordic as a host if you, for example, want to stick with something else that you're already using. Yeah. And this makes a lot more sense if you know what our Wi-Fi IC actually is. Because what we have is, I'm just going to skip this one and go straight here. What we have is a companion IC. So this is an IC that you just put next to a host processor, like, for example, your NI52 or 53 series ICs. And you can add Wi-Fi functionality to an already existing system. Yeah, we have 3 of these devices, so I actually do need to go back to this slide quickly. We have the NF7002, which is a dual band device. That's what I would recommend in most cases. So it supports 2.4 and 5 gigahertz, active and passive scanning. It usually, like, they are meant as station device, so not as access point devices. We do, however, support soft AP if you want to, even though I like Bluetooth commissioning better. And this one supports dual band, is available in QFN and wafer level chip scale, which is good, which means the wafer level chip scale makes it very suitable for modules. I think I saw on the Rutronik page also there's you can already get samples from Menu with a Wi-Fi module from us. We have the 71 series, which is slightly cheaper, just single band if you want a single band solution. And then we have this NF7000, which is weird because it doesn't send any data. The main use for this is just the Wi-Fi locationing that I talked about earlier in this Wi-Fi webinar. We have different development hardware. The main thing I always recommend using is the NF7000 DK. This is the 5340. So one of our multi-protocol SoCs as a host, and has a 7002 next to it. This is a full features development board, Arduino connectors. You can get to all the GPIOs. It has LEDs, it has buttons, it has everything you want. It has an onboard debugger. So use this in most cases. We also have an expansion board. If you're familiar with our Nordic Thingy 53, which is a prototyping platform. This will fit into the Nordic Thingy and add Wi-Fi capabilities to it. You can also just snap off this part here and use it as a impromptu Wi-Fi module if you want to. And then the 7002 EK is basically just the 7002 with an extra antenna here in the form factor of an Arduino shield. So you can just plonk this on top of any development kit that has an Arduino connector and add Wi-Fi functionalities to it. Important is there's no Arduino drivers, so this is for Linux or Zephyr. Application host overview, I'll just let this on the screen for a brief time. So for the 52 series, we support simple Wi-Fi applications, and Wi-Fi to the cloud works, but it's not recommended because you will have very little extra resources left for your main application. 53 series supports a lot more. 54L series, available later this year. will support the same as the 52 series with a bit more to be determined. 54H series will support everything. 91 series, as I mentioned before, only SSID scanning. And then Linux, the driver at the moment is experimental, but everything works. And Zephyr is completely fully supported. Then I think I have 2 more slides, maybe 3. Whenever I showed the power consumption here, most of it comes from our online power profiler. So this is used to, or you can use this to estimate power consumption for certain scenarios of interests. You can just Google Nordic Online Power Profiler. You will find one for Wi-Fi, one for Bluetooth, one for cellular. And this lets you estimate your power consumption. All of this is based on real measured power consumption. It's not just anything that we get in the best case scenario in the datasheet. This is what you can expect, but this is measured in a non-interference scenario, right? If you test the same thing where you have 20 Wi-Fi networks nearby, this will look different. But this is very good for estimating power consumptions. We also have an app that works really well with one of our samples in NF Connect SDK for Wi-Fi provisioning. So this showcases provisioning, in this case, an NF 7002 development kit by using the app. So you can use Bluetooth provisioning. I think NFC is also supported and soft IP provisioning too. And then the last thing I really want to give attention to is our Developer Academy. So we have self-paced online courses going into how to develop a Wi-Fi application. We have some that are on the fundamentals of our, like how to develop with Nordic in general. And then we have this specialized course just for Wi-Fi that'll teach you the basics of everything you need to know to get started with Wi-Fi. And this is also like if you have somebody who wants to take a look at Wi-Fi that might already be familiar with Nordic, but even if they're not, you can have somebody spend a day on this course and they will be able to develop a basic Wi-Fi application afterwards. And you get a nice certificate on LinkedIn afterwards. At the moment, we have, I think we had not yet 1,000 people enrolled. But keep in mind, this is actual engineers working with Wi-Fi now, and they spent 8 to 10 hours of their life learning this, and afterwards gave us a ranking of average 9.3. This is completely free and self-paced on your own time. This is actual engineers working on this. If you use the feedback function that's in there, you will send a mail directly to the person that wrote this course, which is our engineers. And with that, I'm done with my very hasty run through of our Wi-Fi solution. I think we can go over to the Q&A.
Yeah, thank you, Nick, for your for your presentation. Yes, we have a few questions got from the audience. So the first question: where do I start if I want to evaluate Wi-Fi and Bluetooth?
As I mentioned the first time, I would highly recommend starting with the NF 7002 DK. So that has a 5340 on it. So it basically supports most of the use cases. If you want to do cellular together with Wi-Fi, then probably go for the 9151 DK together with the 7002 EK on top. Then you have all of that working. Yeah, and like if you want the Linux host, you can either do the EB, the small one, and just solder that to a PCB, or you can also use the EK for Arduino headers.
Okay, super. Why do you need Bluetooth if you have soft IP?
Yes, so this is a question about commissioning, I guess. So soft IP, the way it works, like in very basic terms, is I have a device, like, yes, this is my battery, it does not have Wi-Fi, but if I were to connect this device with my Wi-Fi network here, I need an interface, and I need to get the information about the Wi-Fi network somehow into this device. The way soft IP works is this device would open their own AP, so their own Wi-Fi network. And then I would need my phone to connect to this one, to connect to the Wi-Fi network, which has several disadvantages. First off, this network that I'm opening by this device is completely open, non-secure. Yeah, it's completely open and non-secure. Everybody can connect to this network if they want to. And I also need to disconnect my phone from the actual Wi-Fi network to connect to this network to send the data over. So there's several extra steps, and it's less secure and it's a worse user experience. But it works and you can use it and we support it, but I highly recommend going with Bluetooth for commissioning, which is a lot more secure and a lot nicer to use for the end user.
Good. Then next question, where to buy development kits? So that's something also I can answer for it. So from Rutronik side, we do have all development kits also on stock. So if you want to have a development kit, just don't hesitate to contact us or our Rutronik sales colleagues. Yes, then there's another question. Can you mention the link to the Wi-Fi Academy?
Yeah, do we have a chat? No. But if you just go Nordic Developer Academy or academy.nordicsaber.com, let me quickly check.
To the Wi-Fi Academy, so I think so. Something you have mentioned before, yeah.
Yeah, it's academy.nordicsaber.com. Let me see if I can. Do we have a chat?
Yes,
no.
Normally, yes. You can.
Let me see. I do have a chat. If I can put this.
You can announce. Yeah.
Yeah. So this is the Academy overall. And then this, I hope you see this all. This is the link to the Wi-Fi fundamentals. So the best way to go about it is if you don't have experience, I would recommend doing the NRF Connect SDK fundamentals course first, which teaches you the basics of how to use all of our software and tools. And then you can go into the Wi-Fi course afterwards. We also have courses for Bluetooth and cellular if you're interested.
Good. I think that was all of the questions. Thank you. And the presentation slides and the recording will be sent out to you afterwards. If you have further questions, don't hesitate to contact your local Rutronik sales manager or direct the wireless department of Rutronik. And then I would like to highlight our next webinars. So starting in the beginning of October, we will have a webinar series with the newest topics about cellular and GNSS. We will have our supplies Telet, Unicore, Kyocera, EVX, and of course Nordic Semiconductors on board. Still, all the information about it can be also found on our Rutronik webpage and will be shared within our social media channel. So thanks again, Finn, for your presentation today, and for the audience, have a nice day, and see you in the upcoming webinars.
Thank you. Bye.